Okay, so let's start. Hopefully the NC State and Duke folks are also online. So I'm very excited to have Kathy here. Big welcome to Kathy. So Kathy is the Henry and Gertrude Rothschild Professor of CS at Columbia University, and she was also the founding director of the Data Science Institute. She served as the director from 2012 to 2017. Before that, she was department chair and vice dean of research in the School of Engineering and Applied Science. So Kathy has done a lot of work in NLP. Her main interests are in text summarization, question answering, natural language generation, social media analysis, and multilingual applications. So a lot of overlap with what students are doing here. She's had numerous awards and honors. She's ACM Fellow, IEEE Fellow, AAAI Fellow, and also founding ACL Fellow. And then she's also had the PCASE Award before it was called PCASE, and the NSF Faculty Award for Women. And she's also won the Columbia Great Teacher Award. Thanks. Welcome, Kathy.
Oh, I have to turn mine. Okay, I think I'm on. Can you hear me? Okay, thanks, Mohit, for inviting me. I'm really glad to be here and meet all of you and hear about what's going on at University of North Carolina here at Chapel Hill. All right, so I'm going to talk today about work that our group has been doing over the last 5 years or so on how natural language processing can be used to address social needs. And since the explosion of text data on the web, we've been interested in seeing how we can make use of these data, how we can exploit these data to address social problems. But as all of you are well aware, text data on the web appears in many different languages, and social needs occur in many different countries. Even when we just look at one language, like English, we find that in online genres, it can be so different from standard American English that we also have to think about strategies. We can almost think of it as a foreign language. So my vision is to be able to analyze social media for insights into events in the world, and then to be able to generate presentations that connect events, personal accounts, and answers to questions. And as with most of the work in the natural language processing field today, we use a machine learning framework. We start with data, which is often labeled, and from that data, we may extract features. We also may look at different forms of representational learning that we can use. And we do this to be able to predict output for a particular task. Now, my research is not in machine learning itself, so I'm particularly interested in seeing what data is available for learning and how we can make use of that for the output. And I'm also interested in what features and representations can yield good predictions. So today I'm going to be talking about 3 different areas of societal problems that we've been working on. The first concerns disasters of various types. The second is, as we move to global information access, how can we address this? And then the third is more recent work that we've been doing where we're looking at social media posts of gang-involved youth. So turning first to disaster, we were motivated to do this when Hurricane Sandy hit New York, and I had many students who came to me and wanted to see how they could put their talents to use for this problem. And so we began with work on developing a system which could provide updates during the disaster. And in this work, we were looking at updates from an objective point of view. What had happened? What is new? So we could think of this as being able to monitor events over time. Our input is streaming data. It can come in the form of news or web pages. And at every hour, we want our system to produce an update which says what's new. So this is harder than it seems. It's actually a lot harder than text summarization, which is an area I have spent a lot of time on, because not only do we want to get things which haven't been said before and are new, but we also critically only want to get salient information that is new. There are a lot of details that are new, and we don't want to report all of them. So ultimately, what we want to be able to do is to track a major event, like an event like Hurricane Sandy, which hits. We can think also right now there are a couple of major events, like the coronavirus would be one. So we want to identify that a major event is hit, and then we ultimately would want to be able to track and identify sub-events that are spawned by this event that comes through. So for Hurricane Sandy, we had, following it, the Manhattan blackout. We had a fire in one of the boroughs of Manhattan, the Breezy Point fire, and we had the public transit outage caused by flooding. And so we'd want to pick up that these occurred following it and that they were related and so forth. So for this problem, we use data that we have gotten from NIST. It was developed as part for what was called the Temporal Summarization Challenge. So this was data that was collected over a 2-year period. It's a web crawl, and it was collected in 11 different categories of disaster. So I'm showing for here protests, terrorist events, I think this is earthquake, and bombings. And the goal is then we get documents in over the course of an hour. Here I show only 4, but there's much, much more. And at the end of the hour, we want to produce a short update which tells what has happened. So in this first update, the generated summary would include information like where, what was the disaster, an earthquake, where it hit, off the Pacific coast of Guatemala, the magnitude of the quake, and so forth. And of course, when we come to hour 2, we now don't want to repeat this information again. So for this problem, we use a temporal summarization approach. We're going to work in time slices. Here we work at an hour. And at each time slice, we're using what's called extractive summarization. So we're identifying sentences in the input that we want to include as part of the update. So in each time slice, we first want to predict which of the input sentences are salient. And to do that, we're making use of disaster-specific features, and I'll tell you a bit more about that. Second, we remove redundant sentences, looking at semantic overlap between the previous hour. We still will end up with far more information that we would want to report as a summary, so we then cluster. And for clustering, we're using a method called affinity propagation, which allows us to incorporate the salience prediction as a prior. So we then cluster, and from each cluster, we'll select an exemplar sentence to include in our update. So what kind of features have we found helpful? We make use of 2 different kinds of language models. First, a language model that we built from a generic news corpus containing 10 years of AP and New York Times articles. And this kind of language model will score sentences by how typical they are of the language. So the higher score means the sentence is more fluent. That's useful in the context that we're in because some of our sentences are coming from web pages, and some of the sentences on the web page will be, sort of extraneous. They could be ads, they could be junk of various kinds, and so this can help us find those that are legitimately part of the information content. But perhaps more interestingly, we use a domain-specific language model, and we build different language models for each type of disaster. So we have one for earthquakes, one for hurricanes, one for terrorist events, and so forth. And this kind of language model will score a sentence by how typical it is of the disaster type. So if we look at 3 possible sentences here, which are all related to this earthquake in Guatemala, using the domain-specific language model, it would score the first sentence in this group higher because it contains phrases like disaster management or local tsunami alert, which are all phrases which are typical of earthquakes. But we don't want to just get sentences which are typical of any earthquake. We want sentences which are specific to the particular earthquake that we're looking at. And you can imagine that in a stream of information when an earthquake hits, we'll also get comparisons to past earthquakes. So we also make use of geographic features. We tag the input with a named entity tagger. And then for each location in the sentence, we get coordinates for those locations, and we measure the mean distance to the event. And sentences with locations that are closer to the event would be ranked higher. Finally, we also use semantic information. So we look at a number of synonyms, hypernyms, and hyponyms of the particular event type. And those sentences which have more of these kinds of words, again, would be given a higher score. So what have we learned? So the red line is our approach, which uses both the AP clustering plus salience, and we compare it against other approaches that were used at that point in time. This work is about 5 years old, so of course since then all the work in summarization has moved to neural nets. But if we look at the x-axis measures days since the event started, we compared it to our approach. The blue line is the AP clustering but no salience predictions. HAC is an approach typically used in summarization, hierarchical agglomerative clustering, and then RS is a ranking to search approach, which would be an IR type approach. And we can see that the salience predictions lead to high precision quickly, before 2 days, and they also allow us to more quickly recover more information. So we have, since this point in time, been looking at developing neural summarization methods for extraction, and in our work we found that simpler is better. So in general we found that if we can use averaging for encoding, we do better than using a more complex model, and that using pre-trained embeddings is just as good as updating. We're also doing current work on how we can incorporate representations of entities and locations into a neural model, as clearly these are key to being able to summarize about events. We can think of an event as usually consisting of being defined by the participants or the people, the location, and the date. So having those representations would be helpful. Yeah.
So I had a question about the previous slide. So for the salience model, what's the ground truth? So how do we know?
Oh, so the ground truth, so this was as part of this temporal summarization track. And there were multiple participants who participated, and NIST was the evaluator, and they identified nuggets, facts that were true in particular time slices as it went through. And the metric is actually slightly different from recall and precision. They're looking at how quickly you can pick it up. So the lag between when it was first known and when a system reported it also goes into the score. Okay, so in addition to looking at objective reports on disaster, we were also interested in personal views, finding out from people who have actually experienced the disaster. And so we were looking at weblogs like this that convey personal narratives of people who have experienced it. And we can see, if we look at this, that it follows a structure which linguists have noted. It starts off with the background. We were sitting down to a late dinner on Monday night when the storm was supposed to hit. It was really windy, but the rain hadn't been that bad. And then we come into this series of complicating actions. This is when things really begin to start happening. So here we have, by 10 p.m., the skies lit up in a purple and blue brilliance, and the power started to go out here and there. That's when I noticed neighbors across the street running out of their homes and fire trucks racing down the block. I saw a steady trickle of water coming down the street on both sides, and then water began pouring in through the creaks in the basement door, so my husband went to grab the pump. And now, finally, in this, we have what is called the reportable event. This is that moment of sort of life and death, the climax of the story, the whole purpose for telling it. So here, he went upstairs to get a tool, and in those few seconds, ocean waves broke the steel door lock and flooded the basement 6 feet high in minutes. So our goal is to be able to automatically identify this reportable event and extract it. And we reasoned that if we could find the sentence that conveyed this most compelling event, it could serve as a summary for what is this story about. Data was an issue here. And so we went to Reddit, and we used the Ask Reddit subreddit. So one example would be with the tagline, "What's your creepiest real-life story?" And we downloaded 3,000 stories, but of course we could have had sort of infinite number of stories. A very small amount of these we had manually labeled by other students in the department, and this is what we call the seed set. But this was a very tedious task. We found it took people a long time to do it. We could only get a couple of hundred stories labeled in this way. And clearly this was not really enough for a machine learning approach. So we looked at making use of distance supervision. And here we made use of heuristics like TLDR, too long didn't read, and it, hypothesized that if we looked at, that's a sort of summary, so if we looked at semantic relatedness between that TLDR and sentences in the summary, we could find the sentence that was most closely like that. We used other heuristics as well. For example, when we have a large amount of comments, what were they most related to, and so forth. So this gave us two kinds of data, small amount of well annotated and a large amount of noisily annotated data. To develop the system, we built on linguistic theory. So Prince has claimed that stories are about change. Livia Pogliani has said that the turning point of a story is marked by change in formality, style, or evidence. And Labov, who had developed this structure of personal narratives, which I showed earlier, said a change in verb tense often accompanies that most reportable of events. So we thought, well, what kind of scores could we have for a sentence of narratives as it progresses that could tell us something about this change? We thought, well, we could have scores representing the syntactic complexity of the sentence. So sentence length might be 1, and we could imagine that, you know, when we get to that point, the climax of the story, that we might have a lot of long sentences, and then all of a sudden a short sentence could mark it. We looked at scores of semantics, the similarity to surrounding sentences, again, hypothesizing that perhaps we would have sentences would be quite similar until, again, we got to that point. And then we also thought about lexical scores, looking at the Dictionary of Affect and Language, which scores words along 3 dimensions, how pleasant they are. So this corresponds somewhat to sentiment, how negative versus positive an emotion are they conveying, activeness. So this would score how intense a word is. And then imagery, how much does a particular word invoke a concrete object in the real world. So this shows here the plotting of a story across time, and here it's plotted each sentence for where it falls on the dimensions of activeness and pleasantness. And you can see that our hypothesis is that the most reportable event should fall at either a min or a max in these scores. So here it would fall at the max of activeness when we get sentences like broke the steel door lock or flooded the basement 6 feet high, and it falls at a min in pleasantness. We did experiment with other features, so tense of the main verb, given what Polanyi had said, and intersentence shifts. We looked at the position of the sentence in the narrative, and we also looked at semantic similarity between the sentence that we were thinking about extracting and the beginning sentences of the narrative, since sometimes the narrative has a summary in the beginning. So what have we learned here? Well, we've learned that change features are the most effective of the different features that we looked at. And we also experimented with how to use the data. So we experimented with a setting in which we trained only on the seed data. So this is a small data set, but accurately labeled. On using distant supervision as well, which gave us a large labeled set, but noisy. And then also self-training, where we first developed a classifier with the seed, and then we labeled additional stories in our data set, and we fed them back into new labeled training data, but only when they agreed with distant supervision. So we made use of it in that way. And we can see that our self-training approach does the best. So some of our current interests, and I have these interests in other genres of summarization that we're looking at, are the abstracts of these kinds of personal narratives are very different from abstracts that you will see in the news domain. There's a lot of rephrasing and paraphrasing that goes on. The personal narratives are told in this very informal style and have a lot of pronouns and sort of free words like well and but and so forth. And to rephrase them so they're readable, there really needs to be a lot of paraphrasing. So we have done work already in looking at developing a neural approach to align the sentences of the narrative with the sentences of human abstracts. And in the future, we will look at making use of that to be able to generate paraphrases in our output. And I think the current abstractive models will not work well on this kind of data because of the extent of paraphrasing that goes on. Okay, so let me turn now to what happens when we're now operating not just in a world where English is the language. So as we all know, these disasters take place around the world. We've seen the earthquake in Nepal or the tsunami in Indonesia. And often where they're taking place are in places where the language that is spoken is what's called a low resource language. This is a language for which we don't currently have machine translation and for which there is not a lot of data available to develop machine translation. So the first topic that we looked at here was how can we adapt our summarization techniques so that we can do what we would call cross-lingual summarization for these low resource languages. So cross-lingual summarization is where you want to summarize in one language a document that was written in another. So for us here, we would want to produce a summary in English of a document that was written in a foreign language. And there are two ways that you could do that. You could either summarize in the low resource language and then translate the summary into English, or you could translate the document and then summarize the translation. So to train a summarization system, we typically need both the document and the summary pairs for a very large number of documents. So if we have to have a document in one language and the English summary in another, and we want to have this for many different languages, you can see that we're just not going to have that data. So this left us with having to take the approach of translating first and then summarizing. But since it's low resource, translation systems, when developed, are very poor. And this gives you an idea of what the input to a summarization system that relies on translation in a low resource language looks like. So we could, as people, could get an idea maybe of what this is about. There's a person named Manja Kumbabi. He's running for a parliamentary seat in the town of Kinondoni. And then he says something about without drugs, so we might guess that that has something to do with what he's working on. So clearly a difficult problem. So what we did was we said, well, if we might be able to use this approach called abstractive summarization, where we're not extracting sentences, but rather we're rewriting, and we might be able to use that rewriting to generate more fluent summaries. So to do this, we created a multilingual summarization corpus by taking a well-known summarization corpus in English drawn from the New York Times, where we do have single document articles published in the New York Times along with their summary, both in English, and we translated those documents into the low resource languages that we were working in, Tagalog, Swahili, and Somali, and then back again into English. And this gave us a corpus where we have a noisy document, and for each noisy document, we have a well-written English summary. So now we have a good data set where the input looks like the kind of document we might be getting from our machine translation system. So the data we had, more specifically, we took 112,000 of these pairs, translated the documents into Somali, Swahili, and Tagalog. We use 2 neural MT systems for this. These were part of, this is part of a larger project that we're working on. And that was the MT for the project. And then we translated back into English again. So we got these sort of synthetic translations, and so you can see here, not as bad. The summary is not as bad as the original ones that we have, but you still have a lot of these sort of odd phrases. He praised the consultation of the community of Kansas City, which half of the participants failed. So it gives us something that looks like what we want. So for this, we then trained an abstraction model, and now we are using a neural net approach. We used a sequence-to-sequence model that has both copy attention and coverage, and it's based on the model developed by Abigail C., which is very commonly used for abstraction. We pre-trained for 12 epochs on the English New York Times corpus, and then we trained the baseline for another 8 epochs on 100K synthetic translations taken from each of the 3 languages we were looking at. We also did mixed corpus training, where we took 100,000 of these synthetic translations randomly and evenly across all 3 languages, and we saved out a validation set for tuning the parameters. So our baseline is just the part trained on the 12 epochs on the English New York Times, and we compared it with different state-of-the-art. You can see we're roughly in the same ballpark. We don't care about being best. What we want to show is what we do after this results in improvement. So we've evaluated in 2 ways. First, we did a sanity check by evaluating on a held-out test set of 6,000 synthetic translations. And this is shown for the ones that the data set of summaries produced by going through Tagalog. And here you can see that both the Tagalog version and the mixed version do significantly better than the baseline. The mixed version does slightly better than the Tagalog version, and that's interesting because that means we can begin to look at new languages. But we also wanted to do a real-world evaluation, so we took 20 web logs from each language, so now these hadn't gone through the synthetic translation. We don't have a gold standard to compare it against, so we used human judges, and we asked them to score the resulting summaries along a scale from 1 to 3. And they had to score both on content and fluency. And we expected it to do better. Now we're showing it for Swahili. We expected it to do better on fluency. But what was interesting was that it actually did better on content also. And we think this is because since people were more easily able to read the summaries, they were more easily able to tell what information was conveyed. So if we go back to our example, here's the original document. And if we look at our baseline system summary, this was trained on English only. We can see that it does a lot of copying from the first sentence. Very little additional words go in there, and we have something that is not much different from our original document. But if we look at our model trained using the multilingual corpus, we can see that it does do some copying again from the beginning, but then it does some rewording so that we get Manja Kamami comments on his plans to vie for Kinondoni without drugs. So definitely gives you a better idea of what the example is about. So what have we learned here? We've learned that summaries are a good target for improving fluency using abstractive methods of summarization. We've provided a new multilingual summarization corpus, and I showed you how it improved on the languages that for which we created the corpus, but we also evaluated on an unseen language, in particular Arabic, from an earlier summarization task, and we saw that for that it also improved. So people who have worked in this area know that abstractive summarization and generation for that model often produces hallucinations, that it hallucinates words for the output that were not in the input, and often this can result in a very errorful, misleading generated text. And so we're interested in seeing what kind of training we can do to avoid these hallucinations. We've done some initial work in a language generation task where we injected noise into the training data and made use of self-training and showed that this could improve on this problem. Let's see, how much time do I have? Do I have right till 5 or?
Yeah.
Okay.
20 minutes.
Okay. So I'm going to go through the next part quickly. I want to leave enough time to get to the last part of the talk, which is my favorite work right now. So we also looked at whether we could make use of sentiment for disasters around the world. And here the idea is if we analyze the subjective posts of everyday people and identify sentiment and emotion in their posts, we could identify where problems still persist. But because, again, we may be dealing with low resource languages, we were interested to see whether we could create these kind of sentiment models without making use of machine translation. And so we used an approach where we would train a sentiment model on a high resource language like English, where we have lots of labeled data. And then we would transfer that directly to a low resource language by placing those tags on the English side of a parallel corpora and training using bilingual word embeddings to transfer the sentiment. And then we evaluate that sentiment model on the low resource language. So we're interested in the transfer medium. How well do we do if we have a parallel corpus of exactly the same type as the data that we're going to be working on? So tweets and about disaster. How well do we work if we have a parallel corpus, that is where we have exact translations of the input sentence in the target language? So we have a lot of out-of-domain parallel corpora if we make use of the Bible or the Quran. But as you can see, this is very much out-of-domain. It's not very close to Twitter. And it's not necessarily about disaster. We were also interested in making use of comparable corpora, so we could get these from Wikipedia, where you might have 2 articles on the same topic in different languages, but not necessarily one-to-one translations of each other, and then also a monolingual corpora. So we did this work on 17 different languages in 5 language families, and for each of these, we looked at creating them as a low-resource language by removing any labeled data that we might have. So some of the most low-resource languages were Tigrinya, Sinhalese, Uyghur, and so forth. Others come from the European Parliament corpus. So they're typically a little more high resource, but we could experiment with them in a low resource domain. Here is our architecture for a cross-lingual model. It's a bidirectional, long, short-term memory network. And the bilingual features that we use are cross-lingual word embeddings, which come in at the bottom. And we also experimented with making use of bilingual sentiment embeddings and bilingual sentiment scores. And then finally, we also made use of what if we had only a monolingual corpus, but we did have a bilingual dictionary, which we could use to translate source words making use of these dictionary entries. This, of course, would be a very noisy translation. We know it wouldn't work well, but it would give us some words in English and some words in the foreign language all in one text. And this is what we would call a code-switched partial translation of the training data. And if we do this, this does allow updating the bilingual embeddings. If we look at our results, this is for the 17 languages that we studied across the bottom. The yellow bars are what would happen, how well a system could perform if we used the labeled data for that language, which we had. So that's in some ways the upper bound, the best that you could do. And we want to see how well you could do with our approach, which translates data across. So this is the gray bars. And we compared with two baselines, majority, which in a text is typically neutral. Most sentences do not have sentiment. Or a rule-based approach where we took like the score of the words from a lexicon and averaged those scores together. So you can see direct transfer does better than either of the baselines, the rule-based or the majority, and it lags behind the supervised version by about 15 points on average. We did learn something about the different kinds of resources. So we did learn if we have an in-domain parallel corpus, that is with translations, you do better, even if it's very small. So the smallest size we had was about 11 or 12,000, which is quite small for this kind of training. And it still would do better than making use of something like the Bible or the Quran or the Wikipedia comparable ones. We also learned that the embeddings are best when learned on the bilingual context, and that the bilingual sentiment embeddings are helpful so long as we have an evaluation data set which has high sentiment content. And our method of creating this code switch data was also quite helpful. So we'll turn now to our last area where we're looking at analyzing the posts of gang-involved youth. So we all know about that firearm-related deaths is a big problem in the U.S. right now. And we know furthermore that this violence disproportionately affects low-income cities, such as Chicago, which had more than 3,000 shooting victims in 2015. So I'm doing this work jointly with a collaborator from the social work school at Columbia, Desmond Patton, and he had been analyzing posts from Chicago gang members for a while and had found that violence was exasperated by taunting between gang members on social media. So this he called the digital street, and he found that there was a parallel between the digital street and the physical street. Furthermore, he found that aggressive behavior was often triggered by trauma, that these people had gone through a lot of traumatic experiences, for example, when friends and family members are shot, and that trauma would often turn around and turn into retribution. He had been studying a girl, actually, named Shakira Barnes. She is a recently deceased gang member in Chicago, and she is someone who became gang involved due to trauma after the death of her friend Taekwon. This incident happened when she was 13, when her friend Taekwon was shot and killed, and she herself was in turn shot and killed at the age of 17 when she revealed her location on social media, and the rival gang members could then find her. And she was somewhat unusual, first because she was so active but was a female gang member. And she was also unusual because she was extremely active on social media. So between this 3-year time period, between 2011 and 2014, she posted some 27,000 tweets, and she had about 4,200 followers on Twitter. So Desmond was analyzing this data set along with the tweets posted by her followers. The language of these tweets is quite different from the language of standard American English. And so you can see 2 examples here. Needless to say, this language causes a problem for NLP systems which are typically trained on the Wall Street Journal. So we developed this collaboration with Social Work, and they had been studying and annotating this corpus for some time. So they formed the annotation team. We had a lot of interaction between the social work researchers and computer scientists. They also often brought in youth from Chicago who were formerly gang involved so they could help us in interpreting the meaning of the tweets. So we started, as we did this work, we had roughly 5,000 labeled tweets from Chikira and her top communicators, and we knew from the work that they had done in analyzing them that context is really critical in interpretation. If you take them out of context, you often can't tell. Even a person who is familiar with this dialect often can't tell what is meant. In addition, we had 1 million unlabeled tweets from almost 280 users. These were all within the social network. This gives you an idea of what that annotation looks like. So here the top one is labeled with aggression, and they did a fine-grained analysis, so they further broke it down into threat and insult. But we could only deal with a 3-way classification. Doing more than that at this point was too hard. And then the bottom one on loss. So the goals for the natural language processing part of it, currently community outreach workers do look at the social media posts of these gang-involved youth, and they intervene when they see aggressive behavior in order to diffuse violence before it happens. They also could intervene at an early point when the loss first occurs. But when they scour social media, they do it manually by hand. So the idea was if we had a natural language processing tool to help, this could help filter some of the tweets that people would have to look at. And so our goal was to be able to automatically predict aggression, loss, or some other category for unseen tweets. And we wanted, since we had a limited amount of labeled data, we wanted to be able to exploit this large unlabeled data set. And we also wanted to be able to use the context of the tweet. So we considered the semantic context of what had been said up to when the particular tweet we were looking at was posted, the emotional context of what was said, and as well who interacted with who. We experimented with a word-level convolutional neural net, and we exploited the unlabeled data in 2 ways. First, by using it to create domain-specific word embeddings, and second, using it to create a lexicon of aggression and loss. So to create that lexicon, we used an algorithm to automatically induce it. This algorithm constructs a lexical graph from word embeddings, so placing words that are more semantically related closer to each other in the graph, and it propagates labels from the seed using a random walk. And we use seed words provided by the social workers. We started off with 29 aggression words and 40 loss words. For the contextual features, we wanted to make use of what the user said, the word embeddings of the tweets that came before, and what the user felt, which we could get from the aggression loss lexicon. And for the hyperparameters, we experimented with the number of days that we looked back, how much context we had, half-life ratio, that is, whether more recent tweets mattered more than ones that were further away in time, the type of post, whether self-tweet or retweet, and then we also looked at different measures of aggregating from the words to the tweet to the context, whether we used a weighted sum, averaging of them, or the max. For user interactions, we looked at whether a user was involved in a tweet if posted, retweeted, or mentioned. And then for each pair of users in the unlabeled and labeled corpus, we aggregated all tweets where the pair was involved, and we averaged the document embeddings to come up with a pairwise user interaction. So this shows the architecture. It's pretty much a standard CNN, except for after max pooling, we concatenate in the context features to the result and use that to do the final prediction. So in our experiments, you can see that making use of the domain-specific word embedding, so this is from building them from our corpus, did well. We compared them against a whole number of different methods. Since we had a relatively small amount of data, we wanted to see, well, if we had Google News embeddings, which were created on much larger, maybe we could do better, and you can see we did not. We tried with an African American vernacular English corpus collected at UMass. That was different, so we can see that having the vocabulary and the wording that was used very specific to this location was important. Even we collected tweets posted at the location right where the gang was centered. That was not adequate because, of course, you would get many people who are not gang involved. They just happen to live in that area. Glove Twitter or random initialization did even better than that. On our user history experiments, for what the user said, we found that representing 90 days back was helpful, and but counting the more recent tweets more heavily was also important. Averaging worked. But when we looked at what the user felt, going back only 2 days was helpful. And here, no half-life ratio was used. Here, summing was more important for aggregation, and we reasoned because it allows us to retain peaks. And this is interesting because these findings reflect the insights from the social work research, that is, that loss precedes aggression in a 2-day window, and emotions fluctuate. If we look at our different models, we compared against a baseline that we had developed previously using a support vector machine, and you could see that we get improvements, significant improvements with the domain-specific resources over the baseline. And when we add context, we get significant improvements even over that. Even if you augmented the support vector machine with context, you got significant improvement over it without. Finally, we also were interested in looking at bias in the model. This is a pretty important high-stakes domain, and if we were thinking about giving it out to community outreach workers, we know that machine learning algorithms have bias, and we wanted to see what we had here. So we first did a systematic interpretation of the model using a leave one out method, and we found, surprisingly, that in 10% of the cases, the stop words like in, on, or da, which is the, can cause the aggression prediction. We tested that further using adversarial testing by inserting and on into every tweet, and we found that when we did that, the prediction flips to aggression in 3 to 5% of the cases. We developed an approach to reduce bias by asking the social work researchers to annotate each of the tweets that they had labeled as aggressive with rationale, shown in yellow, the words that caused them to do that label. And then we incorporated those rationales into the model by training attention in the model on them. And so the ground truth was a distribution among the rationale words, and we used the KL divergent loss, which looked at the difference between what the system was predicting as attention and the rationale words. With this model, we found the F measure, the accuracy, was unchanged in the output, but we had several measures to measure the influence ranking of the tweet words. Here, this is what we called rationale rank, and at the top of the list, so at 0 would be is where you would want the rationale rank words to fall. And so a lower number here is better. And you can see that when we use the rationale rank, we do get a lower number. And we then tested it again by this adversary method, inserting function words into the tweets. And we can see that our method with the rationale at the bottom gives the lowest number of flips, which is, again, what you would want to have. So what have we learned here? Well, first, being able to measure bias is important. Using F measure alone is not enough. So making use of these additional metrics can help us tell whether where we're making errors and why. We also found that integrating emotions and semantic content of context helps improve performance. Exploiting the unlabeled data helps both by using the domain-specific word embeddings and the lexicon of aggression and loss. And we are working with outreach users. This is an ongoing process to see how we can have them use the tool to help. So in conclusion, I hope to have helped to convince you that multilingual and non-standard languages require attention, and that if we make use of semantics, neural architectures, data, and real-world context, we can have a leg up in solving those problems. So I would just close by thanking my current PhD students, the undergraduates and MS students who participated in the work, and my many past students. So thank you.
Questions?
Yes?
Yeah.
So if implemented, would you consider the application of your model a form of government surveillance?
So we don't, you mean the gang-involved youth one?
Any other one?
Oh, any of them. Well, with the gang-involved youth, we don't work with police, we work with social workers. So, but you would have to worry, we wouldn't want our algorithm to fall into the wrong hands, particularly with people who don't understand the logic, the language, or the, or the implications. So the rest, I haven't thought about it. I mean, I suppose any tool can be, if put in the wrong hands, can be used the wrong way. Yes.
So I have two questions. One was about the personal stories of disaster. So there, you said low pleasantness score was indicated.
Yeah.
Is that tied to the domain, or is that?
No, we're just looking for min and max is all. So it could be, wouldn't necessarily have to be low pleasantness, it's low anything. Oh. In that particular example I was showing, it had a low pleasantness score. But our hypothesis is, following the linguistic theory, that at either a min or a max is where you would find it. So you could imagine a story building to a climax of either something really horrible or something really great.
So a change in pleasantness.
Yes, over the course of the story.
The other question is about the first part, about disasters, where you were temporarily summarizing
news and weblogs.
So there, were you making any kind of Markov assumption where this current summary would depend on what was summarized previously? Because if it's the same thing being repeated, it might not be interesting.
Yes, so we do check for redundancy between the current summary and what was, so we had features in there to remove redundancy. Yeah.
So I forgot to ask if there is any questions from Duke or NC State. I think they were having some WebEx connection problem. So we saw full rooms attending your talk, but I don't know if they can ask questions. Sometimes that needs a second channel. Sorry, go ahead, Shashank.
Kathy. So my question was, so in the first part where you were summarizing streams of news stories, so there the assumption kind of is that the order of reporting would be the temporal order of relevance, right?
So yes and no. Yes, I mean, it doesn't happen that way. I mean, people repeat what already happened. And so that's why we have to do this redundancy check to remove what was already reported. It would be a question of, if something came in the next hour, we don't specifically test for temporal relations within the text. So, it would be, even if it wasn't reported in the last summary, we might have known about it from the input documents for the last, hour, and we could not, we might have the chance of including that information. So that is a sort of negative of this approach. Yeah.
Any last questions? Okay, since we are, it's around 5:10, let's thank the speaker again.
Okay.